Hello guys, welcome once more to another video in this channel. So in this video you are going to be looking at the Northwest Regional Mock 2022 further maths paper 2 question 8. The question reads: A. Use the ratio test to determine whether or not the series is sum from n equal to 1 of n factorial on 2n ordered factorial converges. 4 marks. B part, the sequences an and bn are given by an plus 1 is equal to 1/5 into an plus 8 and bn is equal to an minus 2. Roman 1, show that bn is a convergent geometric sequence and express bn as a function of n. 5 marks. Hence, Roman 2, find the limit of the sequence an. 3 marks. So let us see how to solve this problem. So we dive straight away into the solution. Alright, so we begin with the first part of the equation. So question 8a. 8a is asking us to use ratio tests. Very important. They have specified we are using ratio tests to determine whether or not the series converges. Now, so let me just write using ratio tests to verify if the series. Now this is a series that has been given to you. Remember, a series is simply the sum of the terms of a sequence. So n factorial on 2n factorial is a sequence, and then the series is a sum. So using ratio test to verify if the series converges. Alright, converges or not. Okay, so that's what we want to do. Now the ratio test, let me just try to brief you guys on what the ratio test is about. The ratio test says that, so just like a hint. So let me just give you guys a hint. Given, let me just say, a series v of n, which is the sum of terms of a sequence. So the sum from n equal to 1 to infinity of maybe the sequence u of n, for example. Alright, so I'm giving this series be a series. Now the ratio test says that, so from the ratio test we have that. Alright, the first thing is that if the limit, so we are going to be computing limits. If the limit as n tends to positive infinity of the absolute value of u of n plus 1, u of n is a sequence, divided by u of n. If this limit is less than 1, then the series v of n converges. That's what we should say. Now, if this limit is greater than 1, so the next thing is, if the limit is greater than 1, then the series v of n diverges. So it diverges when the limit is greater than 1. Now if the limit is equal to 1, so the instant when the limit is equal to 1, we cannot conclude. So we simply say the test fails, so we cannot use the test. Then the test fails, that is, no conclusion about the series, about the convergence or divergence of the series. Alright, so now we see that if we want to use the ratio test to determine whether or not this series converges, we must begin by looking for this limit, and then we use these 3 conditions to conclude if the series converges, diverges, or the test fails. Alright, so suppose that our u of n is equal to this n factorial divided by 2n all that factorial. So our u of n is equal to that. So we need to look for u of n plus 1, because we see that in each of these formula u of n plus 1 is part. So it means u of n plus 1 is u of n plus 1 is just gotten by replacing n with n plus 1. So in the place of n here, in the place of n factorial, I'm going to put n plus 1 ordered factorial. So n plus 1 ordered factorial divided by in the place of 2n plus 1, I'm going to put 2 into n plus 1, then all that factorial. That's it. So that is our u of n plus 1. Now we need to look for this limit, so let's just copy the limit. So this limit is equal to, now or better still, let us find u of n plus 1 divided by u of n. So our u of n plus 1 divided by u of n, so u of n plus 1 divided by u of n is equal to, this is u of n plus 1. We are going to simplify to cancel out things, then we are going to divide it again with u of n. This is u of n. So let me write it in a better way, so I can rewrite it like this: u of n plus 1, and then I'm going to use the division sign itself, so divided by u of n. So we can reverse, so it's times, now the denominator of u of n goes ahead, goes up, and then the numerator goes down. All right, so that's it. So let's try to simplify this. So it means that u of n plus 1 divided by u of n, what is it? Let's simplify. So u of n plus 1 divided by u of n is equal to, now n plus 1 factorial can be written as n plus 1 times n factorial. Now 2 into n plus 1, all that factorial is the same as 2n plus 2, all that factorial, then times this numerator, this remains the same. I'm still going to rewrite it, so I have this. Alright, so this is going to be equal to, now we see that n factorial is going to take care with n factorial. So let me just change the color, maybe I put it in red. So anything in red are the terms that will fall off. Now next we are going to now get this numerator, which is 2n all that factorial. So we have 2n all that factorial divided by 2n plus 2 all that factorial, 2n plus all that factorial, then times this guy here, n plus 1, so times n plus 1. Alright, so from there now we can also try to simplify 2n plus 2 all factorial. So 2n plus 2 all factorial can be simplified to 2n plus 2 times 2n plus 1. So you have 2n plus 2 times 2n plus 1, then times 2n all that factorial, 2n all that factorial. Alright, so let's also multiply with our n plus 1. Okay, so we are getting closer to getting a simplified version of un plus 1 divided by u of n. So un plus 1 divided by u of n will be equal to, so we see this in red, that is 2n all factorial, is going to wipe with this 2n all factorial. So the 2n factorials are going to cancel. Now when they cancel, we are going to be left with n plus 1 divided by 2n plus 1 times 2n plus 2. Yeah, that's what we get. So now in this 2n plus 2, we can factor out a half. We can factor out 2 from there. So the numerator is n plus 1. Now the denominator, you have 2n plus 1. Now in 2n plus 2, we can factor out 2, and we are going to have n plus 1. Now doing that, you see this guy falls up. N plus 1 cancels with n plus 1. So finally we have 1 divided by 2 times 1 divided by 2n plus 1. So that is our un plus 1 divided by u of n. Now we need to look for the limit, and then we use these various conditions to conclude if it converges, diverges, or the test fails. So this limit is just equal to the limit, since you already have un plus 1 divided by u of n. The limit as n tends to plus infinity. In the place of this, I'm just going to replace it with all of this. Alright, so clearly we see that as n tends to infinity, the denominator will be tending to infinity, so the reciprocal will be tending to 0. So this gives us 0. So since it is 0, so let's try to draw now a conclusion. Since this limit, that is equal to 0, and 0 is less than 1, then we can conclude that the series, that is our general series here, this guy, it converges according to this. So according to this first condition, it converges since that limit is less than 1. This series converges by the ratio test. Alright, so we are done with the first part of the problem. Now part B has two questions. So let's first of all collect the data. We have two sequences, an and bn. So an has been given. So part B, we have an and bn has also been given. That's bn. Now let's begin with the first part of the equation. So Roman 1 of part B. Roman 1 is asking us to show that the sequence bn is a convergent geometric sequence, and we express it in terms of n. So we are showing that bn is a convergent geometric sequence, and expressing bn as a function of n. Now bn, so let's begin with the first part, showing that, so let's first of all show that it is a convergent geometric sequence. So showing that bn is a convergent geometric sequence. So we are required to show that, two things. We first of all show that it is convergent. So we first of all show that it is geometric, and then we later on show that it is convergent. So showing these two, then we have shown that it is convergent and geometric. So we are required to show that bn is geometric and convergent. So let's begin with bn being geometric. So for bn to be geometric, we just need to show that the ratio between any two consecutive terms is a constant. So we use the n term. So the ratio between bn plus 1 and b of n should be equal to a constant, and that constant is a common ratio. So let's look for bn plus 1 divided by b of n. So bn plus 1 divided by b of n is equal to, now since we have b of n, this is b of n, so we can find b of n plus 1. So b of n plus 1 is just going to be a of n plus 1 divided by a of n plus 1 minus 2, sorry. So this is b of n plus 1, now divided by b of n. Alright, but we know what a of n plus 1 is. It was given a of n plus 1 is this. So we just replace a of n plus 1 where we see a of n plus 1. So we have a of n plus 1, replacing it here, then we have minus 2, then all divided by a of n minus 2. So let's simplify. So the numerator, you're going to get 1/5 of a of n plus 8 divided by 5 minus 2. its denominator you still get a of n minus 2. So simplifying the numerator, you get 1/5 a of n. So let's just rewrite the denominator, a of n minus 2. Now 1/5 a of n. Now 8 on 5 minus 2 is negative 2 on 5. Alright, so we see that we can factor out 1/5 in the numerator, and factoring it out, you're going to have a of n minus 2, and in the denominator you're still going to have a of n minus 2. Now the a of n minus 2 cancel, so I'll put it in red. So at the end you get 1/5. So hence b of n is geometric, since we have a constant at last. Now next we are going to show that it is convergent, and then we conclude that it is geometric and convergent. So showing that it's convergent, we just need to show that the absolute value of the common ratio, that is the absolute value of b of n plus 1 divided by b of n, is always less than 1. It's always less than 1. Alright, so since we have our b of n plus 1 divided by b of n to be 1/5, and the absolute value of 1/5 is less than 1, then b of n is convergent. So we are done. Now the next part of the equation is asking us to express b of n as a function of n. Alright, so next we are now expressing b of n as a function of n. So since b of n is geometric, it means b of n is just going to give us the very first value of b. Now we need to check. So according to the definition you are given, you can look for so the very first value of b is b0, is going to give us e0 minus 2, but there is no idea about a0. So a0 is actually 4. So I forgot to include it in the equation. So a0 is 4, so we should take note. Alright, so with that we can get our, we have our b of n is equal to b0 times the common ratio, which is r raised to the power n. Alright, so from there we have, since we have our b of n is equal to a of n minus 2, we can get b of 0 is going to be a of 0 minus 2. A of 0 minus 2. Now the common ratio is 1/5, so we have 1/5 all raised to the power n. So since a of 0 is 4, 4 minus 2 is 2, so you have 2 times 1/5 raised to the power n. So that is b of n in the terms of n. So we are done with the Roman one of part B. Now hence, mark this word hence, meaning that we are going to use the information that we have had previously. So we are finding the limit of the sequence a of n. So that's the objective. So Roman 2 is to, so Roman 2, we are using a hence problem. We are finding the limit of the sequence a of n. So to find the limit of a sequence, we need to know what the sequence is. So from we have b of n, sorry, not m, b of n is equal to a of n minus 2. We can get a of n. So it means that our a of n is simply equal to b of n plus 2. But we know what b of n is. This is b of n. So b of n plus 2 is just this plus 2. Now we can factor out 2 and we get 1 plus 1/5 raised to the power n. So it means that the limit of a of n is the limit of that equivalence. Now the limit of a sequence is simply the limit as n is tending to positive infinity of a of n is equivalent to the limit of this a of n here, so the limit of all of this. Alright, so since 2 is a constant, we can pull it out and then we evaluate the limit of the interior. So alright, so this limit, now when n is tending to positive infinity, 1 on 5 raised to the power n is tending to 0 because the interior here is less than 1. So since it is less than 1, then raising it to the power n is going to be tending to 0. So the interior here is going to be tending to 1 plus 0, which is 1, and everything is going to be tending to 2 times 1, which is 2. It means that the limit of the sequence a of n is equal to 2. So let's write the final statement. Hence, the limit as n tends to infinity of the sequence a of n is equal to 2. Now let us verify. Actually, we are done with the equation, but let us try to verify if this is true. Now let's come back to our a of n. Let's come and verify something. Now this is a of n plus 1 in terms of a of n, is it? Alright, so let's try to verify something. It is clear that as n tends to infinity, as n approaches infinity, positive infinity, we have a of n plus 1 is approaching a of n. So this means that we can compute the limit on both sides. So the limit of a of n plus 1 will be the same as the limit of a of n. Alright, so let me just say, let maybe the limit of a of n be equal to L. So this will be the same as the limit of a of n plus 1. Alright, so this means that we have this. So computing limit on this left hand side, we are just going to have L. Now computing limit on the right hand side, you're going to have 1/5 into L plus 8. So 1/5 into L plus 8. So multiplying both sides by 5, it means that we are going to have 5L is equal to L plus 8. So this means that we can subtract L on both sides. 4L will be equal to 8, meaning that our L is equal to 2. So our answer is correct. So the limit of a of n is equal to 2. So the question actually never asked you to just find the limit of a of n. It said, hence find the limit of a of n. So if you use this other method, it is going to be marked wrong because you never use the hence. If they said hence or otherwise, you can use this method as an otherwise method, provided you don't know what to do. But when a question says hence, you just use what you have had previously. So this is what is required. But this is now, I try to use it to show you that to verify if this answer is actually correct.